Hi, I'm Dean Remsburg, and I'll be teaching you everything you need to know about regenerative braking. This is an important concept to learn about because it is very important innovation that is used to make all sorts of vehicles more energy efficient. Regenerative braking is used to boost efficiency in electric and hybrid vehicles, like this Rivian R1T and Porsche 919 hybrid Le Mans race car. To see how the system works, first let's do a little breakdown. Here we have John. Let's say John is driving a traditional combustion-powered vehicle, say a Ford F-150. John is traveling 30 miles an hour, and his truck weighs about 4,000 pounds. Using this simple equation, we can calculate John and his truck's kinetic energy. Plugging in the weight of his truck in kilograms and his velocity in meters per second, we can see that his kinetic energy is 153 kilojoules. For reference, your cell phone requires about 1 kilojoule of energy to be used for an hour. Now let's say John is going 60 miles an hour. John doubling his speed made his kinetic energy increase by 400% to about 613 kilojoules. Now John comes to an intersection and the light turns red. John slows his truck to a stop and his velocity becomes 0. This means that John's energy goes to 0. But where did all of John's valuable energy go? Well, when John pressed the brake pedal, the pistons in his brakes applied a friction force to the brake disc, and then all of that energy dissipated to the atmosphere in the form of heat. Now let's say instead of an F-150, John is driving a Tesla Model 3. Again, he's going 60 miles an hour before coming to a red light and slowing to a stop. John's Tesla weighs about the same as an F-150, so the kinetic energy was again 613 kilojoules before John started to slow down. But the Tesla has a little trick up its sleeve to conserve some of that energy so it doesn't entirely go to waste. Instead of just applying the friction brakes, John's Tesla first slows his vehicle using the regenerative braking system, and this saves John 70% of that energy that entirely went to waste in the F-150. This means that 430 kilojoules of that energy was instead put right into the Tesla's battery to be used again when the light turns green. Over the course of a longer trip, the amount of energy that John is saving becomes very valuable. In fact, in a post on TeslaMotorsClub.com by a user named Randy, Randy showed his ECU data from his entire time owning his Tesla. It showed that just under 15% of Randy's entire charging input since he bought the vehicle has been from regenerative braking. This means that if John drives 100,000 miles in his Tesla, he will have driven 15,000 miles on purely recycled kinetic energy. But just how does John's Tesla magically recover this valuable energy? Well, let's take a look at the inside of an electric motor like the ones in John's Tesla. Two magnets surround the motor, one north and south. These magnets surround coils of wire that are connected to the battery and have current running through them. The current running through the coil induces a magnetic field, and the coil will rotate so that the induced magnetic field aligns with the magnets on the exterior. As more coils are added, they can continue to rotate, which rotates the drive axle, as you can see here in this animation. This motor can also be run in reverse. If the axle is spun, it induces a magnetic field which causes an induced current in the coils, which sends energy back to the battery. As the vehicle accelerates, battery power runs current through the motor, which translates the electric energy into rotational energy, and the vehicle moves forward. When the gas pedal is released, the rotational motion of the axle is converted by the motor to electrical energy and sent back to the battery, all while slowing the vehicle by magnetic resistance. Then John can press the friction brakes much later than in his F-150, and he retained a lot of energy. But this regenerative system is just one of the 3 general types of regenerative systems. The system that Tesla uses is known as an electromagnetic regenerative braking system. This system was first developed by the Sprague Electric Railway Company all the way back in 1886. It has been used to power electric trains for over a century. It is also the most developed of the 3 and most common in road vehicles. It works in fully electric vehicles like John's Tesla, or it can work in parallel to a combustion engine in a plug-in hybrid like this BMW 330e, or in a parallel hybrid like this Toyota Prius. Second type of regenerative system is what's known as a flywheel KERS, or kinetic energy recovery system. It simply consists of a flywheel with lots of mass and its own transmission, connecting it to the drive shaft. The flywheel hybrid system, or flybrid, was invented in 2006 by John Hilton, who at the time was a powertrain development engineer for Renault F1 and the reigning world champion Fernando Alonso. The flybrid system is a very simple one. The flywheel transmission simply applies the clutch when the throttle is open, connecting the flywheel shaft to the drive shaft, which begins to rotate the flywheel. The flywheel is spun in a vacuum to limit heat and friction losses. It can be spun to a speed of anywhere from 20,000 to 50,000 RPM. This, along with its heavy mass, gives the flywheel a great amount of rotational energy. Then when braking occurs, the clutch is depressed, and the car comes to a stop while the flywheel continues to spin. Then when the car starts to accelerate again, the clutch is reapplied, say coming out of a slow corner, and the energy from the flywheel is translated back to the drive shaft, which boosts the power of the wheels. Here, engineering YouTuber Tom Stanton built his very own flywheel KERS bike. This shows in action how the flywheel system works. As he pedals here, the flywheel gains momentum, then he stops and the flywheel continues to spin. Then when he reclutches the flywheel, its momentum is enough to power the wheels to accelerate him. We watch it again here. He builds up some energy in the flywheel. He stops and it continues to spin, and then it moves his bike. The flywheel system is also easily paired with an electric motor to increase the efficiency of the system and increase the torque output from the conserved energy. A couple of race cars that have competed using the flybrid system are the Porsche 911 GT3R and the Audi R18 Quattro e-tron. The R18 even won the 24 Hours of Le Mans at the hands of Mr. Le Mans himself, Tom Christensen, using the flywheel electric motor configuration in parallel to a turbo diesel V6 engine. The flywheel system is an incredible innovation in endurance racing as it relieves a great amount of wear on the brakes. The development of the system for road car use has been quite limited due to hesitancy to have a 20-kilogram wheel spinning at 50,000 RPM involved in a passenger vehicle crash. Third and final type of regenerative braking system is hydraulic launch assist. HLA was developed by the Eaton Corporation in the early 2000s and is comprised of three main components: fluids and gases, a fluid reservoir, and an accumulator. Under braking, the fluid in the reservoir is pressed into the accumulator, which compresses the nitrogen gas, causing it to have a lot of pressure. When the vehicle begins to accelerate, the nitrogen gas pressure is released and the fluid is pushed back into the reservoir, and the force of the gas directly applies energy to the drive shaft. This system has been implemented in heavy transit industry because it can be easily fitted to a combustion-powered vehicle without any new electrical components being added. This makes it a cheap solution that can increase fuel efficiency by around 40%. Eaton Corporation has partnered with the United Postal Service to fit their HLA system on delivery vehicles in the UPS fleet across the country. In summary, each regenerative braking system has its own pros and cons, which make their optimal usage different. For electromagnetic, its high efficiency and safety development make it the best system for road car use. The flywheel's ability to store huge amounts of energy make it an excellent solution for racing use. And hydraulic's ability to relieve pressure from braking systems as well as cost make it a great solution for efficient heavy machinery.